In this video, I'm going to talk about state response of a model. I don't know why I wrote twice here. Okay, state response of a model. Now we know that x dot equal to ax plus bu. That's a state equation. Here I am using small letters because I'm assuming a and b are the scalar quantities. So a and b, these are scalar quantities. Now x dot is nothing but dx by dt. I'm going to say this is in time domain, time dependent quantity, so I am including t in there, assuming it's a time dependent quantity. Now I'm going to multiply by e to the power of minus at on both sides. So e to the power of minus at x dot t equal to e to the power of minus at a times xt plus e to the power of minus at b times u of t. Now I'm going to move this e to the power of minus at times a x of t to the other side. So e to the power of minus at x dot t minus e to the power of minus at xt equal to e to the power of minus at b times u of t. Now on the left hand side, this is same as d to the power of derivative of e to the power of minus at x of t. So I used this principle, d by dt uv equal to du by dt v plus u times dv by dt. So by using this principle, this is what equivalent to the above block. Now I'm going to integrate on both sides. So when I'm integrating it, I'm integrating from 0 to t. So the inside t becomes tau. I need to use another variable, so I'm using tau as another variable. Somebody is using some other variables. Okay. So now on the left hand side, the equivalent of integration is e to the power of minus at x of t minus x0 equal to integral of 0 to t e to the power of minus a tau b u tau d tau. Now I'm going to multiply with e to the power of at on both sides. So x of t equal to, or x of t minus e to the power of at x0 equal to e to the power of at integral of 0 to t e to the power of minus a tau b u tau d tau. Now after rearranging, x of t equal to e to the power of at x0 e to the power of at integral of 0 to t e to the power of minus a tau b u tau d tau. Here a is a scalar quantity, so what I'm doing, I'm going to change that scalar quantity to matrix format. So instead of small a, I'm going to use the capital A. So x of t equal to e to the power of at x0. So that's a zero input response. Okay, so here x0 is the initial condition, assuming, say if it is a electrical circuit, assuming that capacitor or inductor energy storage elements, they have some energy initially stored in them. That's the zero input condition. Zero initial conditions are e to the power of at. So here the initial conditions I'm assuming 0, but input is given. When I say 0 input, I'm assuming input is 0, but initial conditions are not 0. When I say 0 initial condition, here I'm assuming input is there, but initial conditions are 0. Okay, so we know that e to the power of at is nothing but state transition matrix. So x of t equal to state transition matrix. I'm representing phi of t or phi of t. Phi of t equal to e to the power of at x0 plus, so this is a zero input response, e to the power of at integral of 0 to t e to the power of minus a tau b times u tau d tau. Okay, so this is zero input, zero initial condition response. So this is the total response of a model or system. So in this video we learned that we learn a formula for a state response of a model with zero input conditions and zero initial conditions. Okay, but this is the total response of a system. Thank you.